This is the peak lecture. I'm sorry, the fifth lecture. And we're going to cover peak oil, energy return on investment as applied to things like oil, and the limits to growth. And we'll give a lecture for 1 hour, take a 5-minute break, and have questions after that. And please think of questions as you go along and write them down so we don't have awkward silences. Okay, now, when I started as a graduate student, we didn't have questions of this type. Most of what we had in the name of conservation had to do with Teddy Roosevelt and Gifford Pinchot and trees, and so forth. It wasn't much thought about how long non-renewable resources would operate. And an important thing that had happened was, as I will cover next time, economic thought had come along that more or less belittled or did not consider issues of depletion, of running out of things. And even pollution was not highly considered when I was in graduate school. Obviously, things have changed a lot. And so I'm going to talk about how this change came to be. One fateful day, I was wandering around in the bookstore as a graduate student, and I came across this book that was just really, for me, eye-opening. And in fact, there were people, not many, who had been thinking about resources in general, and they had come together under the purview of the National Academy of Sciences and put together this book in the old pre-political correctness time, Resources and Man, obviously Resources and People. And in there, I found an amazing paper by this guy, Marion King Hubbard, who I actually got to know pretty well. In fact, Paul, one year he visited my class in systems ecology on my birthday, which is in fact May 3rd. I'll be 80 in 2 days. And we had a birthday cake and Hubbard visited our class. But here he is when he was a bit younger. And he worked for Shell Oil in Columbia University and some other places. And we came up with this concept of peak oil. I don't think he used the term. And it really is focused in a different way on resources. It's focused not on running out, but on the pattern of use over time. So here's a nice little thing that's, as every beer drinker knows, the glass starts full and ends empty. The quicker you drink it, the sooner it is gone. And whoa, the same principle applies to oil and gas. And if you think about it, economic growth is drinking that oil more quickly. And it is a very big thing. And when I read this, at that time, I was totally focused on fish and water and stuff like that. I thought, wow, this is really important. Why doesn't anybody else talk about it? Why aren't people thinking about it? And Hubbard said, well, just look at fossil fuels from the perception of human history. Lord, the steam engine was invented before the beginning of this Hubbard's pimple. This will be the use of all fossil fuels over the human experience. And the human experience obviously goes back a lot further than Stonehenge or Greek culture or pyramids or whatever. And it's just a blip in the history of humanity. And I thought that was just amazing. And so he came up with, and what he did was he introduced the idea that you would not simply use something and then it would be no more. But what you do is that you develop a resource over time. And he started with oil with, in his mind, I guess, Drake's well in 1860 or so, and growing initially exponentially as more uses are found for it. And then at some point, no longer being able to grow exponentially, and you would reach a peak, or he said later, perhaps 2 peaks or even more. But you'd reach a peak, and then you would have a more or less mirror image decline. Now, we didn't have much experience at that time with this decline. But he made this pronouncement originally in 1955 that the United States would reach a peak oil, and everybody would say, well, that's crazy. I mean, look, it's growing. It's not only growing fast, it's growing exponentially. And how can you talk about any limit to the production of oil? And so he made this graph a few years after his original pronouncement, and there you have it. And whatever happens, the integral under this curve is all the oil that's available. You can use it faster, you can use it slower, but you can't use more. Well, I saw that and I thought, this is a whole new way of thinking about civilization. I said, for crying out loud, I'm going to be alive in this time period. And why isn't anybody thinking about this? And then he said, for the world, depending on how much oil we had, and he really didn't know, we might have a peak as early as 1990 something or 2000 or something like that, depending on Q infinity is the total amount of oil that there might be. So I said, oh, I'm going to still be alive in this graph. Now we're going to take a look at what the graphs actually look like. Hubbard was right in principle, wrong in detail, or you might say quantitatively wrong. But well, we're going to take a look at whether the future, how well it's borne them out. One thing that we did understand was that the rate of use of oil was declining from the red to the green to the purple to the blue curve. So that's clearly taking place. This is an early graph, and it indicated that even if we develop the Alaska wildlife oil, it wouldn't add very much to our total oil production, which we had thought back at the year 2000 would have been declining by then. And that's the curve. I guess you can see my cursor just fine. Now, the economists did not like this at all. They thought any resource scarcity would be compensated by lower use, because the price would be higher, technological changes, and substitution. And they were bolstered by a paper by Barnett and Morse, who said that of some dozen raw materials, only one of them, forest products, had become more expensive over time. In other words, they said, well, if things are getting scarcer, if raw materials are getting scarcer, it's not showing up in prices, so you don't have to worry about it. And that basically means that we're right. Now, there's a little circular reasoning in there because they had to use inflation corrected prices. And inflation, if it's driven by resources, there's a very interesting circular argument there. Okay, now in 2006, I made this graph, and it looked like for the United States, Hubbard, who incidentally said very clearly, this is only for the lower 48. He said, I heard there might be some oil in Alaska, but I don't know any details. So his prediction was the yellow. The green is for the lower 48, which is pretty close to Hubbard's prediction. We could say that in 2006. And then there's this bump on Alaska, which saved our hiney back then. And well, still is to a small extent. So, but at that time, in 2006, it looked like Hubbard was fairly close, at least in the general pattern of his prediction. His values are the yellow, and the actual for lower 48 are the green, and they're dropping like a stone. And then Alaska began to drop like a stone. And so at that time, this was 1980, I guess this was 2000 and something. It was looking pretty grim, and we had very active what's called ASPO, American Society for Peak Oil, for the study of peak oil. And we are European ones, and people were very concerned. But then something happened. And this shale gas and shale oil, they're mostly, I couldn't find a shale oil graph, but it's pretty much the same thing. And most important were the Barnett, and here in the Permian Basin, and up in Montana and in North Dakota, we had the Bakken formation. And down in Louisiana, the Haynesville and Eagle Ford, these are somewhat important also. And at this time, or before this time, when this was happening, the economists said, don't worry, technology will come along and there will find a substitute. Well, I didn't know what that substitute would be. And it was obviously shale oil. And I lived in Montana at that time, so I paid a lot of, or I guess at that time I was going to Montana for summer, and I would drive through this area and look at the amazing development of the Bakken field in North Dakota. And something that I stumbled upon was that the size of the fields were not the same. That there were sweet spots in there in green, Montreal County, for example, and then a lot of the other areas had much, much smaller fields. So the question was, how big were the sweet spots? You couldn't do this just anywhere. And turns out, here's a sweet spot, in this case, in Texas. And there's an oil, each one of these square patterns is an oil rig. And let me tell you, there's a lot of them. And you have to keep drilling them because they only last at high volume for a couple of years. And so we're drilling them a lot. But the thing is that we're running out of sweet spots, and that's starting to make a difference, and we'll take a look at that. Now, I go to a site. I should put this on our own site, so you can do this if you want. I go to a site maintained by the United States Geological Survey, and it shows the production of oil every week. Now, this low point was that low point I showed you from Hubbard's graph. And the original peak of Hubbard in 1970 was about 12,000 here. Well, this fracking thing developed, I think, by George Mitchell, and I'll explain what it does, has made a huge difference, and there was a big increase, and then a bit of a falter, and then it dropped during COVID because demand dropped greatly during COVID. And now it's recovering after COVID, although for the last little period here, it's been essentially flat. So I look at that every week and say, have we reached the new peak oil in the United States? And the answer is tune in. We don't know yet. But certainly we've had two peaks. This is our second peak. And will we ever get to be more than that? I doubt it very much. And there's a lot of, if you keep track of the oil literature, there's a lot of attention paid to the fact that they're pretty much running out of sweet spots. So looks like we have a second peak. And let me tell you, a lot of people don't like oil very much for various environmental and climate reasons, and they're good reasons. But had this fracking not occurred, and had the Russian-Ukraine situation been playing out as it is now, the United States would find itself in a much tougher position because there's not a lot of extra oil in the world. We're producing about as much as we use now, but we'd only be producing about half of what we need without this fracking. Now, what is fracking? I meant to put in a picture. I didn't. It's you drill a vertical well down about 2 miles, and then they have technology to turn the bit. And then you drill horizontally for 2 more miles. And you're intercepting, instead of a real oil field, you're intercepting what's called not source rock, but what is it, Paul? Anyway, capture rock. Rock has some oil dispersed through it. It has often low permeability and low volume for oil within it. But if you go through it 2 miles through the formation, and then you put down explosives and crack the rock, and then you put tremendous pressure behind it, it's a very complicated factor. You can get out a decent amount of oil. And this is where we get half of our oil now, with this very, very technology and resource and energy intensive process. Okay, now I'm going to back up a little bit, and I'm going to say right now, we're going to look more explicitly at peak oil in a little bit. But right now, I want to tell you a bit about my own journey in figuring out where we are with oil, because I thought this was an incredibly important issue, and we didn't have much information about it. So in 1981, I had, with Cutler Cleveland, we'd worked out this paper that was published in Science magazine, which is, the place to publish if you're a scientist. And we looked at yield per effort and net energy analysis. In other words, we took the ideas I've been working on with fish and applied it to oil. And we'll talk about what we found out then. So I had some credibility in the field. And then a friend of mine pushed me to get involved with ASPO, Association for the Study of Peak Oil. And that made a huge difference in my life. And I went back. I've been studying tropical forests and carbon at that time. And I went back and got interested again in oil. But I didn't know very much about what had gone on. And I needed to learn a lot. And so I went to a meeting that was in Lisbon, and I met this guy, Jean Larrère. And I said, he's and his colleague, Colin Campbell, this is the guy that knows about oil. And in fact, he was head of exploration for the giant French oil company, Total. And so I went and visited him at his home in France, in the middle of nowhere in France. It was his family farm. Beautiful place. Liked it very much. And I found out that the only reliable information on oil in the whole world, on oil supplies, was in that upper quarter of his farmhouse. There was no other reliable information anywhere in the world. And this kind of scared me. And so I learned as much as I could from Jean, and he's become a close colleague of mine. I interact with him on email more or less every day, and we keep plugging, and we'll show you. Now, the first thing I learned was that the solid bars. Now, this is for what we call regular oil. It doesn't include fracked oil, and it doesn't include the heavy oil that they have in Canada and Venezuela. But here we have a pattern over time, which we found oil, which is the highest bars, and then the black is the pattern at which we used oil. And what became very obvious to me very quickly was that around 1980, we started using more oil than we were finding. In the 50s and 60s, we were finding much more oil, but that the finding rate was declining. And, you know, this goes back, or we're going to talk about David Ricardo, the economist, about diminishing returns. But almost anything, Ricardo worried about farmland, that we'd use the best farmland first. But here we found the best oil fields first. And then they would go down over time. Now I'll show you an update of this graph in a little bit. This is what I learned from Jean. The data, especially the official data, is extremely unreliable. It's tainted for many reasons, including money and political power and other things. Second, to get the official amount of oil in the world that's remaining for us to produce, or that has been produced, Oil and Gas Journal calls up in early December various political entities, normally the Department of Energy for each of 40 or 50 oil producing countries. And they ask him, and they tell him, and that's the number they use. In other words, it's not derived, well, some countries like the UK, it's derived by good geologists, but mostly it's a political statement. And um, this gets published as official reserves. And each year there are what are called revisions and additions. And the revisions and additions were oil fields that were often found decades before. So they weren't found in that year. They just said, well, it's a little bit bigger, a little bit smaller than we thought. And they'd add that in. And we'll show you what an incredible difference that makes. In many large fields, which supply half the oil of the world, half the oil in the world comes out of only 400 fields out of the many hundreds of thousands of oil fields that there are. So, and many times they suddenly crash. Now, at one time, the Cantarell field in Mexico was the second largest oil field in the world. And its production essentially disappeared in a matter of just a year or two. So that's another thing I learned from John. I also learned something called Hubbard linearization, in which you could take the annual production over the cumulative production expressed as a percent and plotted against the cumulative production, which is essentially time. And that intercept could give you an estimate of how much oil there was. Now, I obsessed over the mathematics of this for several years and wrote several papers that I didn't publish on it. Because if you can tell how much oil is left, it's really important. And my answer now is, well, all I can do is tell you that empirically, Hubbard linearization is within 10 or possibly 20%, about 20% of the time. And sometimes it fails, but very often it's very good. Now, in order to know if it works, of course, you need to have a completely exploited resource. So we have a Hubbard curve, a hump-shaped curve for Pennsylvania anthracite, and it's all gone. It's all been mined out. And the Hubbard linearization predicted the total amount that you'd get very accurately. And we have that for some oil fields. And so sometimes, most of the time, it works pretty well, and sometimes it doesn't. You just have to accept that. Okay, but wait, the official reserves of oil are going up and up. And here they are from British Petroleum, that until this year was giving estimates of how much oil. And the Oil and Gas Journal, their estimates are going up and up. Their brown line here. The World Oil and OPEC, all of them give estimates of how much the oil reserves are. You see, they're getting more and more every year. So we don't have to worry about oil, right? And that's the view presented to the world. Okay. Now, eventually, Jean, myself, and we added in Roger Bentley, who knows a whole lot about oil, published this paper this year. How much oil remains for the world to produce? Comparing assessment methods and separating fact from fiction. So I'm going to try to tell you my best view of how much oil remains in the world. And here we have this graph I showed you before, the finding of oil, and in the red line, our use of oil, and the integral of the area between the red and the green, which is getting larger, cannot be greater than the integral here, which is, in other words, we're basically not finding oil as fast as we're producing it. We're just pumping out this excess that we found back in the 1950s and the 1960s. Okay, now, I told you that the official keepers of the world oil were adding revisions and extensions on the year that they found them. And what you should do is add them to the year in which the oil field for which the revision and extensions were made the year of the original strike. And when you do that, this is, instead of our reserves increasing over time, they peaked around the year, here I go, 1985, and are declining. So we have only half as much oil left to pump out of the ground as we thought we had, or as we had in 1985. In other words, we've used up half. And it's going south, and we have update to that continues to go down. So that's the first thing that we found. Then we used hybrid linearization. This funny little third point is the COVID year that throws all the data wacky. And we made some estimates of how much oil we thought we would find. Now, one thing we found out is that you had to pay a lot of attention to what's real oil. This is real oil. Crude oil, we call it. And then increasingly, the official keepers of oil have been adding in light tight oil. That's the frac stuff. So if you go from 3,000 to 3,500 gigabarrels of oil, if you add in that, and this is adding in the Venezuelan and the Albertan, what's called tar sands, which we're probably not going to produce most of that, but who knows? We might get desperate. And we end up with our guesses. This purple is real oil. Real oil, as essentially as Hubbard said way back when, has been more or less flat, except for COVID. That's this big jump. It's gone up just a little trickle since then. It's been flat since 2005. You add in the light tight oil, the fracked oil, and you get this light blue. That's some. You add in the extra heavy, the Venezuelan and Canadian. And what's really going on now is our official oil estimates, people are adding in what is called natural gas liquids, which is not oil. But it's butane, pentane, propane, hexane, heptane, octane. It's stuff that falls out of natural gas. The oil, the real oil, appears to have peaked for the world, and it's declining. That's the purple. But the gas production is still increasing and is probably going to increase for another 20 or so years. And natural gas liquids are increasingly extracted from that and mixed in with heavy oil to give us something that we can make diesel and gasoline from. So it's a complicated picture. You can't say it in a simple way. I'm going to skip this graph. Where is the oil remaining? Well, this is an old graph, but it's probably pretty much true today, mostly in the Middle East. And the heavy oil in Venezuela, if that's the case, Canada should be bigger, I guess. And Russia, obviously, is very important. Obviously, oil is more and more important geopolitically. Here is the most recent production of oil done by Matt Mushalik. And what's happening is spatial. That Asian oil has peaked, Mexican oil has peaked, European oil has peaked, Central and South America has peaked, Africa has peaked, US conventional oil has peaked, and so forth. Russia and Saudi Arabia and a few other countries have not peaked. So this will have, I think, enormous implications as we go into the future. U.S. natural gas liquids is way at the top is the blue, and tight oil is this light brown golden color. So the fracking has saved our tail. It's whether you like it or not, and it's good and bad components of it, it's sure made a big difference. Question is there anything else? Because it looks like we're reaching the end of our fracked oil. Now, I could spend a whole lot of time on this, but I'm not going to. With John Halleck and a few others I've looked at, back in 2002, that's the vertical line here. We published in a series of projections of how much oil each of the 46 oil producing countries, major oil producing countries in the world, major and minor, would be. And we made estimates with their low, which is purple. I'm looking at Yemen now, that's the clearest. The low, the medium projection, and the high in the dash and dotted blue line. And what we found here is that for essentially every country, oil producing country of the world, they had a peak in oil production that had occurred or we projected would occur. And and these were different estimates of low, medium, or high of how much oil each country had, and almost always the low predictions were the most accurate. In the United States, for conventional oil, you see between the low and the medium projection was the most accurate. So the take-home message from this very comprehensive analysis, which we've updated for several times, is that some 38 of 46 oil-producing countries have had peak oil. So Hubbard was right in this sense. Whether or not we've had peak oil for the world, we have clearly had peak oil for most oil-producing countries. Another thing we found out when I started working with John, this is for the United States, is that the amount of oil that's produced, which is this line with the squares, is almost independent of how much drilling you do. So the economists will say, well, the price of oil goes up, which it did in the 1970s, and it'll be more valuable. People will spend more effort getting it. Well, we spent a lot more effort drilling for oil, but it didn't change the decline over time of production. So, and here we did it again in 2000, and again, that made no difference on conventional oil, although the fracking did. So it gets a little tricky. Okay, we're going to go back to New Hope Creek and my PhD work on energy return on investment. This is the second major topic I'm covering today. I'm going to do it for time, okay? And remember, energy return on investment is energy delivered to society or the fish or whatever, versus the energy put into that activity, which is usually considered energy invested from society or occasionally diverted from society. And this is a paper we published in 1981. And here is the main results of that paper, which are not exactly correct, but are sort of correct. The red is the energy cost we found for drilling for oil. And the lower two green lines are for oil alone, our return, the barrels found per foot. I'm sorry, this is done in barrels found per foot drilled. You drill a foot, how much oil would you find in that time? And it had declined dramatically from around 40 barrels per foot to around 20 barrels a foot. If this is including the gas found as well, it basically doubles your yield. And this is just the oil. And we did a linear projection. We should have done a exponentially declining, I think, projection that the cost of the oil would be the same as what you'd gain from the oil. Well, we haven't reached that yet. So we were right in principle and wrong quantitatively, but we're approaching that as time goes on. This was on the first page of the Wall Street Journal. And who was it? Woody Allen or no? Somebody said we all get 5 minutes of fame. That was my 5 minutes of fame, and quite a story. But then we started importing a lot of oil, and even though the oil size, the size of the oil fields we're finding in the U.S. declined dramatically, and the energy costs kept increasing, we still are able to squeeze out oil at an energy profit. And I can't tell you what it's been since 2007 because the United States government has stopped keeping the data that we need to make the calculations. So that's one of the things I can tell you is we used to have really good data on resources, and it's a tragedy that we do not keep that data anymore. But almost certainly the EROI is still declining. Okay, now here's some studies that we did. This is for Norway. Norway is the most important oil find since the 1960s. And so this is over time. We did a study in around 2010 with Lena Grandel. This is the oil we found. You see, they had a peak oil around 2000. And this is the gas found, and this is natural gas liquids, and this is condensate. So that's the energy found. Here's the energy cost, which was increasing during this whole period. The amount of energy that was used for this process was increasing, and the energy return on investment for oil only or oil plus gas, whichever way you want to assess it, was declining and has continued to decline. It was pretty high for a while, 40 to 1. It was down to 20 to 1 by 2010 for oil alone. It's probably down to 12 to 1 or so for now. I don't know. I don't have the data. News of the study got around, and I was invited to present on this to Parliament in England. So one of my, again, 5 minutes of fame. And this was a very exciting time. So here I am, looking a little smug, I think, giving testimony in Parliament. And there I am again. And they had, these are many of England's best oil analysts. So they didn't just accept what I was saying, and the parliamentarians are over on the other side of the room. Not too many came. But this was pretty interesting. So I did the same thing for British oil. Remember, the North Sea is half Norwegian and half English, half UK. It's probably more Scottish than English. And this was the analysis that we'd done for the United Kingdom. As I showed you, we'd made projections with the low estimates of total oil, the medium, and the high. how much would be produced over time, and the blue and the purple is use. And as you can see, the actual data followed the low estimates of oil for this country. So UK is basically by now, it's producing only, I think, about 20% of what it did at its peak. And that's behind all the economic problems you're hearing about England right now, and all the strikes of the teachers and the nurses and whatever. There's no energy to produce the wealth that they used to have. Their big oil fields, their Brent and their 40s, they're depleted, they're gone. And then you see this is the total they produce, with each little slice being a particular oil field. The original ones were big, and then they went after smaller and smaller oil fields, and guess what that means? Well, the energy, this is the production and on this axis, and cost was kept constant. So of course, the energy return on investment went down, down, down. And this is what I presented to Parliament. And later studies have come along and pretty much reinforced what we did, a little bit lower. But so other independent English scientists have confirmed what we found, and that has, of course, continued. For the United States, the dots are starting back in 1919. These are 3 different studies of ERI for the United States. There's a little bit of uncertainty. The different studies come up with a little bit different numbers here, but it peaked at somewhere around 20 to 30 to 1. And the last hard number we have is about 12 to 1. And we assume it's continuing to decline. This is for Norway, and this is for Mexico. So all of these studies are indicating that the energy return on investment for our major oil countries are declining, probably much less so for the countries with the really good oil fields like Saudi Arabia and Kuwait and Russia. And incidentally, this decline in quality also applies across the board to copper, which is going to be really important in the future if we have an electrical future, lead, zinc, gold, and so forth. All of them are declining ore grade. Percentage of the ore that is the mineral is declining dramatically over time. So these are big problems that we have to face, and that I'm going to talk about how different economic approaches do or do not deal with this decline in resource quality. Now, I haven't even included in the energy cost the cost of environmental destruction. This used to be all marsh, productive marsh in southern Louisiana. This is the Venice, the circular thing is the Venice oil field at the mouth of the Mississippi River. And all of this has been destroyed principally by oil operations. So if you included that in the cost, the energy return on investment would be considerably lower. Now, energy return on investment will strongly influence net economic growth, cost of government, ability to pay back debts, ability of conventional economic models to work, value of pensions. All of these will be influenced by declining energy return on investment and declining oil production. Okay, part 3. The major study that was done about declining resources is the limits to growth. And I don't know how many of you have heard of this, but I'll give you a review. The original concept was derived by this guy, Jay Forrester of MIT, and he has in his hand an example of some of the first, what's called random access memory, i.e. computer memory, that was ever made. And he has a grid of wires that cross with little iron donuts that are either charged or not, and would store either a 0 or a 1. And at the base of all this digital technology that we're using right now. He was the guy who started that, and he also started the concept of the limits to growth. He originally published it as something called the counterintuitive behavior of social systems, which is an amazing, amazing paper, which I read. My father gave it to me. Since he's an MIT alumni, it was in the MIT Alumni News, and it was just an amazing thing. And so this was handed off to his graduate students and a few others. Vanilla Meadows, who might have been the greatest brains of the group, I'm not sure. And Dennis was certainly a very smart guy, and who I know well. I still interact with him. Jorgen Randers and William Behrens, I don't know much about. And she was just a wonderful person, Vanilla. And their basic graph is this, the standard run. And this would be time, and they would have the human population growing, reaching a peak, and declining. Food per capita growing and then declining. Pollution growing and then declining. Resources being cumulatively used up. So resources are being used up over time. And this was the basic computer model that the basic model of the limits to growth. And this sold something like 20 million copies. It was enormously influential. It was talked about in colleges and universities all over the world. We certainly talked about it when it came out in 1972. And then the oil crisis hit, and everybody thought, oh my God, this guy's right on the money. Well, the only way that this group, the Meadows group, could stabilize the model was to stabilize the human population and stabilize, and this was the real tricky one, stabilize investments. Because if you stabilized investments, you didn't run through the resources too fast. And they tried 50 other ways of trying to save the world, so to speak, in their computer, and they could not. And so they had to both stabilize the population and stabilize investment. Now, you can imagine this was not very popular with the economists either. And they hated it because they said we didn't have human innovation, human imagination in this model. And when the violent oscillations that they had predicted did not occur, they said the model's wrong. The model we can't pay any attention to it. So that was what sort of what happened. It just left the scene. So here's one of the things that they said. One of the criticisms of this, and a devastating critique from the perspective of economists. And of course, a lot of people believe the economists. You know, they went to Yale and so forth, and But the critics didn't understand the timing. One of the things I did that I thought was fairly clever was the variable scale Xerox machine and a ruler. And about the year 2000, I said, well, wait a minute, these oscillations are not supposed to have occurred yet. The model still looks like it might be pretty good. And myself and John Day published a paper saying, well, the model's still fairly accurate. And even up to 2025, well, is the food per capita decreasing in the world? Some would say it is. Population's still growing. Industrial output per capita, well, it might be stabilizing a bit, but it's all messed up with COVID. We don't quite know yet. Here are other estimates done by Graham Turner that came up with similar conclusions to what we did. But something not even, given that it was 30 years later, was not too bad. Model was not too bad. But we don't know about whether we're going to go down this hill or not. Well, Mother Nature, we got to remember, holds the high cards eventually. She will decide what happens. What about technology? Well, you could say no, most increased drilling did not increase oil production. But horizontal drilling did for a while. Where are we? Who's right? And we're going to talk about this in the next few things. Now, I think while the world is looking at climate change and CO2, the depletion is a greater problem. I'm not sure I'm right, but I think I'm right. And nobody's talking about depletion, and everybody's talking about climate change. And in many ways, of course, they will reinforce each other. So that's going to be an interesting thing. Okay, I'm going to end, let's see, almost 1 hour, almost perfect. I'm going to end with this model I made, coming back to energy return on investment, showing you what it means economically. Okay, now we start in 1949. We have the US economy, which I keep, it has to exist in the world. And the economy produces GDP, this green stuff. Now I look at it as this, imagine it, we call it the cheese slicer model. And imagine this is coming out of the economy is GDP. And we slice it. What are we going to do with it? Well, there's really only two things you can do with GDP, especially if you ignore a little bit about international trade. You either consume it, that means you buy a car, you go to a movie, you buy your staples, your food and housing and so forth, or you invest it. You can't do both. And if you consume more, you have to invest less and vice versa. Okay, so of the investments, you must invest in getting the energy to run the economy. You got to pull the energy out of the earth to run the economy. Incidentally, I published this paper in 2009 with Bobby and Billy, a couple of my really bright undergraduates. Now, you have to invest in infrastructure maintenance, fixing your roads and bridges and so forth. And we see that the president's economic plans have a lot of attention to that. And then you have discretionary investment. Then you can invest in a new golf course or a new whatever it is that you want to invest in a new house, I suppose. Okay, and likewise, consumption is either staples, you got to buy them, or it's discretionary. You spend that money to go on a trip or go to a movie or whatever. Now that's 1949. Now we're going to look at what happens to the GDP. So we go to 1970, it doesn't change very much. Little bit more discretionary investment. And then the first oil crisis comes. And look at this top blue line. All of a sudden, we have to invest more into energy, which means that there is less available for discretionary investments and a little bit less for consumption. And the economic times got tough in the 1980s. But we more or less recovered again. So, and by 2007, energy was pretty cheap, no problem. But we projected into the future, if EORI continued to go down, you see the investments required into energy would become much larger and would start squeezing out all consumption, especially discretionary. Incidentally, it was data up to 2007, and this is just our models. And then if the EROI went way down, you see we have to take most of what we produce, or maybe half of what we produce, and use it to get the energy that's necessary to live the rest of time. Now, is this going to be true? I don't know. We're going a bit in that direction. Europe is going very much in this direction as energy is becoming more and more expensive in Europe. Okay, I like this. Nature is going to do whatever it does, whatever we want. Okay, I'm stopping there after 1 hour. Okay. Now, I would think that what I've just said, maybe it's stuff everybody knows, or maybe it's not. But I would think that it has a lot of implications for ultimately people's personal lives, and there might be some questions about it. And it's there's a group of scientists that I would say are not very many that are very concerned about this, and most of the world has no concern at all. In fact, they want to reduce our use of oil and other fossil fuels to protect the climate, or for some other reason, perhaps a legitimate one. So where do we go from here? Okay, Ann, you have your hand up.
I just wondered about the availability of oil or gas with accessibility, I guess, as we're thinking in terms of more in the Arctic area. As things are melting and maybe it's easier to get in and drill. I don't know. Is there any resource underestimates for fossil fuels in that part of the world?
Well, we know we're going to find more gas and oil. And a lot of the stuff that the Russians are exploiting now are in the Russian Arctic. So we know that's going to be true to some degree. The answer is yes, but we're already doing it. I mean, after all, our Alaskan is in the Arctic, and we're talking about now about the Arctic Wildlife Refuge is in